that's that. Good morning. Hello. Welcome back to my stream. Let's see. What are we doing here? Switch and go. All right. Right. We had left off in the middle of this editor thing. But today we're going to do a little crafting interpreters. So that's over here. That's right. We were going to work on superclasses next. The last thing we worked on was all the methods, being able to write methods inside the inside a class. What do we have? And then the initializers. That's right. So now classes can have initializers, and we were timing the initializer call because we had made a little optimization to the initializer that turned out to make things a little bit slower, which was exciting to see. Yeah. All right. My Rust code is probably not the best design because it's based off of the C code, so maybe it would be interesting to go through and rewrite everything from a Rust point of view at some point, and then see if that goes any faster. What do we have here for oops? So we have an initializer here, and oh, I see that. Then it's not supposed to. Let's see what this does. Yeah, not a method. Okay, so that's still working. That's good news. Cargo build release, right? And then no default features. And then what I do is I run for I. Nope. Here it is. We run all of the locks things that we'd gotten so far and make sure nothing panics. Oh, see, that only took 27.99, so 2.7 seconds. And what were we seeing before? Oh, the method call time. That's different. Okay, method call time. Where is that? I can't. Oh, that's right. It was up here. But, so this is interesting that this, we're seeing it, 27.99, whereas before we were seeing higher numbers, right? This was the init code? No, that's the method call time code. Where's the init code? No, it's still method call time. All right. I'm not going to worry about it. I'm getting distracted. Let's dive into superclasses and see where we can go from there. Kelowna, hello, and Shiloh, how are you? Good to see you. Okay, sorry. Yes, as I was saying, distracted. So let's read about superclasses. This is the very last chapter where we add new functionality to our VM. Oh, really? I wonder what else we have then if we're not doing any more functionality. Oh, that's right. There was the optimization chapter. Okay. We saw how well that went last stream. We've packed almost an entire locks language in there already. All that remains is inheriting methods and calling superclass methods. We have another chapter after this one, but it introduces no new behavior. It only makes existing stuff faster. Make it to the end of this one, and you'll have a complete locks implementation. That only should not imply that making stuff faster isn't important. After all, the whole purpose of our entire second virtual machine is better performance over JLocks. You could argue that all of the past 15 chapters are optimization. Yeah, I don't know about that, because basically rewriting it in a brand new language with the new architecture is not just optimization. It's okay. Some of the material in this chapter will remind you of JLocks. The way we resolve supercalls is pretty much the same, though viewed through CLocks' more complex mechanism for storing state on the stack. But we have an entirely different, much faster way of handling inherited methods. Much faster way of handling inherited method calls this time around. We'll kick things off with a method inheritance, since that's the simpler piece. To refresh your memory, locks inheritance syntax looks like this. Oh, the little less than sign, yeah. Here the cruller class inherits from the donut, and thus instances of cruller inherit the cook method. I don't know why I'm belaboring this. You know how inheritance works. Let's start compiling the new syntax. All right, so let's start get status. We're clean and we're up to date. Let's go here. Class declaration is right here. Here's named variable. Okay, so this is the current class business that we had to modify with this stuff. And then here's the named variable. So now we're going to check to see if there's a less than before we do anything. So if self is match token type less than, or is it just less? I've forgotten. It's probably just less, right? Yeah. Then we're going to consume it. Oh, we're going to consume the identifier. Right, and then variable false, whatever that means. We're gonna have to take a look at this and refresh our memories here. A self named variable, class name, which we got from up here, and false, and then self emit byte opcode inherit, which is a new opcode. What does variable do? It just grabs the previous token and calls named variable on it with can assigned, and we're passing in false. We're not in an assignment situation. And the named variable, sets a local versus a setting an up value for it. And then if can assign, then it could be expression. Otherwise, we just do a get. Okay. I think I remember now. After we compile the class name, if the next token is less than, then we found a superclass clause. We consume the superclass's identifier token and call variable. That function takes the previously consumed token, treats it as a variable reference, and emits code to load the variable's value. In other words, it looks up the superclass by name and pushes it to the stack. After that, we call named variable to load the subclass doing the inheriting onto the stack, followed by an op inherit instruction. That instruction wires up the superclass to the new subclass. In the last chapter, we defined an op method instruction to mutate an existing class object by adding a method to its method table. This is similar. The op inherit instruction takes an existing class and applies the effective inheritance to it. Previous example, when the compiler works through this bit of syntax, the result is this bytecode. So we get the class, we define the global for the class, we get donut, we get the class, and then I guess we pop those when we do the inherit. Before we implement the new op inherit instruction, we have an edge case to detect. If identifier is equal. Oh, you don't want a class can't inherit from itself. All right, so do we have that currently? No, we don't. That's a brand new function. I'm just scanning forward to see if that's here, but I don't see it. So maybe that's on value. We could just check for equality. Right, they're both strings. So EQ just compares the strings. Okay. We can try it. What is class name? Oops, I meant Shift K. It's a token. So we're trying to compare tokens. And then we have to see if the lexemes are equal. And parser previous, I think, is also, let's find out. Let pref is equal to parser previous. Clone. And that's also a token, right? Right, and then we can say if class name Lexeme is equal to prev Lexeme, right, it's public. So we can just reach right in there. Then we just can return an error, self error, a class can't inherit from itself. Easy enough. This won't build because we don't have the inherit. Oh, I guess we have to do that. Yeah, we don't have inherit, and that's the only error. Okay. So now on to the new instruction. Interesting, with the way we implement method inheritance, I don't think allowing cycles would actually cause any problems in CLOCs. It wouldn't do anything useful, but I don't think it would cause a crash or infinite loop. Okay. All right, so in chunk, our final instruction, I think, inherit. There are no operands to worry about. The two values we need, superclass and subclass, are both found on the stack. That means disassembling is easy. Oh, I got to add it down here. And then over here, we'll just, it's a simple instruction. So I'll copy that guy, inherit, just like that. Okay. The interpreter is where the action happens. Let's pop over there. Opcode, inherit. Okay. All right, from the top of the stack down, we have the subclass and then the superclass. We grab both of those and then do the inherity bit. So grabbing the superclass peak 1, the subclass as peak 0, table add all. That's a new one. That's class, superclass, methods, subclass, methods, and then pop the subclass. I guess we leave the superclass on the stack. Okay, well, how do we do all the peak stuff? Because that requires a little bit of stack manipulation, right? I look for other places where we call peak. Right, so are we going to validate that we actually have a class? I guess not. I guess the only way it can get to this point is with the correct things on the stack. Unless there's a serious bug in our code. But we can do this, right? Instead of instance, we say peak 0 is going to be the subclass. And then peak 1 is superclass. And these aren't instances. These are classes. Right? I wonder why it's done like this. I don't know. Okay, and then we want to make sure we do the pop. Okay, I'm just going to close these off for now. So pop, and then we're done. And we need a table add all. So that probably means, oops. Let's change this to a C. And change this to a C, else panic. No superclass found on stack. And this will be C, else, panic, no subclass found on stack. Right? Okay. And then we're going to want to add all of the superclasses method to the subclass. And I think I'm just scanning forward here. Oh yeah, superclass must be a class. Okay, so we can at least do that one. But table add all. I'm just scanning forward for that code and I don't see it. And I didn't think we wrote it before because we never needed it before. So I'm a little puzzled where this is coming from. But basically we're going to convert all the methods over, right? So let's go take a look at the class code. And the class has a ref cell of a hash map. So what we can do is we can say copy methods, right? Pub fun copy methods into self. Oh, it doesn't have to be mutable. Self and then superclass self. Can I do that? And then all we do is say superclass dot copy methods. No, subclass. Copy methods from superclass. Probably like this. And I forgot semicolons on those two lines. And I forgot the bang after the panic. Okay. So for copy methods, that should be straightforward, right? We're just going to walk the methods of the superclass and shove them into the subclass, right? So we can just say for m in superclass methods dot borrow. Can I just do that, or do I have to say iter? Does it automatically know it's an iter? And we can say self dot methods dot borrow dot insert, oops, bar mute dot insert m. Oh, I have to get the key value, right? KV. And that's all that should take. Doesn't like that because it's not an iterator. Can I say iter here? Nope. Nope. Expected string found ampersand string. Oh, okay. Yeah, what is it, clone? It's saying to do toString, but I think that does it. And then this is RC found reference. What did it find? Oh, okay, so I should be able to say RC clone the value. Yeah. And I should have known that. I should have known all of that. Okay, so I think that's this. From the top of the stack down, we have a subclass and the superclass. We grab both of these and do the inherit bit. So where clocks take a different path than jlocks. In our first interpreter, each subclass stored a reference to its superclass. On method access, if we didn't find the method in the subclass's method table, we recurse through the inheritance chain, looking at each ancestor's method table until we found it. For example, calling cook on an instance of Kriller sends jlocks on this journey. Nope. Walk up to the superclass, found it. That's a lot of work to perform during method invocation time. It's slow, and worse, the farther the inherited method is up the ancestor chain, the slower it gets. Not a great performance story. The new approach is much faster. When the subclass is declared, we copy all of the inherited class's methods down into the subclass's own method table. Later, when calling a method, any method inherited from a superclass will be found right in the subclass's own method table. There's no extra runtime work needed for inheritance at all. By the time the class is declared, the work is done. This means inherited methods calls are exactly as fast as normal method calls, a single hash table lookup. Well, two hash table lookups, I guess, because first we have to make sure the field on the instance doesn't shadow the method, right? I've sometimes heard this technique called copy down inheritance. It's simple and fast, but like most optimizations, you get to use it only under certain constraints. It works in locks because locks classes are closed. Once a class declaration is finished executing, the set of methods for that class can never change. In languages like Ruby, Python, and JavaScript, it's possible to crack open an existing class and jam some new methods into it, or even remove them. That would break our optimization because if those methods happen to a superclass after the subclass declaration executed, the subclass would not pick up those changes. That breaks the user's expectation that inheritance always reflects the current state of the superclass. As you can imagine, changing the set of methods for a class defined imperatively at runtime can make it hard to reason about a program. It's a very powerful tool, but also a dangerous tool. Those who find this tool may be a little too dangerous gave it an unbecoming name, monkey patching, or even less decorous duck punching. All right. What about method overrides? When copying the superclass's method onto the subclass's method table class without subclass's own methods? Fortunately, no. We emit op inherit after the op class instruction that creates the subclass, but before any method declarations and op method instructions have been compiled. At the point that we copy the superclass's methods down, the subclass's methods table is empty. Any methods the subclass overrides will overwrite those inherited entries on the table. All right, so let me go back to the VM because I'm now concerned because we're cloning the superclass here and then copying stuff here. We actually want to stick them in the class. And I'm looking here, so defined method is what we want to emulate, right? It is cloning the value. Oh, but because the class, yeah, the class is pointing to, is an RC, so it's pointing to the actual class. So that works. Okay. So this should work, right? Should we test this out? This SQ doesn't call cook, but we can call it, right? And we can just say var c equals new c dot cook c dot finish. This should work. Cargo run cook. Oops. No, I have a semicolon there. Oh, I put the word new on there. There. So that worked. So it was able actually on the instance here. Oh, donut's still on the stack. That's supposed to get popped off the stack, right? We did have a pop instruction, but only one pop. We leave the superclass on the stack. When does the subclass get popped off the stack? Because it looks like it doesn't. It looks like it hangs around forever. Is that a bug? Or is that something I just haven't finished yet? Did you notice when we added method inheritance, we didn't actually add any reference? Oh, yeah. Let's finish this up here. This should be able to cargo run detect that class. Oh no, not class. It panics right now. No superclass found on stack, and so we're going to change that to a runtime error here. Okay, let's fix that before I go any further. So this is just self runtime error. Superclass must be a class. And then we return. Oh, did we just, oops, did we just return? Yeah. So we just put that there. Does runtime error return an error? It does. So I could just return that. Oops. Go like that. We could say return that. Okay, saves a line of code. And now suddenly we have a problem. Oh dear, oh dear, oh dear. Right. So I think we have to extract it. Okay, I guess what we can do is this. Pull this all inside. Put it right in here. We don't need this anymore. And we can just say Superclass. Get rid of that. And then, does that fix the problem? Nope. Because now we're doing a mutable thing there. Okay, so both ways don't work. Okay, so how do we get around this issue? Right, because we're doing a mutable in an immutable borrow here, and then we're mutably borrowing things here in order to report the error. This takes a mutable reference to self, and the only reason it needs to do that is why? Because the reset stack. I guess the other option would be to make stack a ref cell, but that would make things even slower. There's nothing else here except for the reset stack requires that to be mutable. Okay. (107). There we go. All right. What's a good way to solve this one? All right. So let's take a look. Superclass is borrowing an immutable. Well, the mutable borrow is here. And then while that's still mutable, and the immutable borrow might be used here when that temporary is dropped. And runs the destructor. So even though we're returning here, we still have to drop the temporary. It might have to run a destructor, which means it needs a mutable. We are cloning this out, though. So if we clone it out, it shouldn't maintain the reference to it, right? What if we separate this? We'll just say let peak 1 is equal to here, and then we can check it here, right? Like this, just peak 1. Oh, now we have 39 errors because I forgot to close something. What did I do? Oh, I left this like this. Yeah, okay, so separating it out like that allows peak 1 to have the clone, and then we can extract it here and not have to worry about that. So let's just call it superclass value. There. Yeah. And now if we run using these two lines again, it should not panic and just report an error. Superclass must be a class. Perfect. All right, so that was section 29.1. Git status, git add source, git commit -m, section 29.1. and it was called Inheriting Methods. All right, good. Even Clippy likes it. Did you notice that when we added method inheritance, we didn't actually add any reference from the subclass to its superclass? After we copy the inherited methods over, we forget the superclass entirely. We don't need to keep a handle on the superclass, so we don't. That won't be sufficient to support supercalls. Since the subclass may override the superclass method, we need to be able to get our hands on the superclass method table. Before we get to that mechanism, I want to refresh your memory on how supercalls are statically resolved. May not be. Presumably the method has been overridden. Otherwise, would you bother to use super instead of calling it? Okay. Back in the halcyon days of JLOCs, I showed you this tricky example to explain the way supercalls are dispatched. All right. So let's keep this. All right. We're inheriting from B. We're inheriting class C inherits from B, class B inherits from A, and A has the method. We're calling test. Test is calling class C's test, which is class B's test, which calls super method, which calls that. So this won't work at all, right? Cargo run, tricky, because we don't have super yet. Yeah. We're not parsing super yet. All right. Inside the body of the test method, this is an instance of C. If supercalls were resolved relative to the superclass of the receiver, then we would look in C's superclass B. But supercalls are resolved relative to the superclass of the surrounding class where the supercall occurs. In this case, we are in B's test method. So the superclass is A, so the program should print A method. This means that supercalls are not resolved dynamically based on the runtime instance. The superclass used to look up the method is static, practically lexical property of where the call occurs. When we added inheritance to JLOCs, we took advantage of that static aspect by storing the superclass in the same environment structure we used for all lexical scopes, almost as if the interpreter saw the above program like this. Each subclass has a hidden variable, storing a reference to its superclass. Whenever we need to perform a supercall, we access the superclass from that variable until the runtime to start looking for methods there. We'll take the same path with CLOCs. The difference is that instead of JLOCs' heap allocated environment class, we have the bytecode VM's value stack and up value system. The machinery is a little different, but the overall effect is the same. So we're going to add a synthetic token called super, okay? And that's right after we begin scope. No, not right after we begin scope. Just before we call it op inherit. Here, okay, found it. Wow. So a self begin scope, self add local. Now the synthetic token, super. Do we want to make that a function of token? Like that? And then self-define variable 0. We're assuming it's going to be 0. It'd be nice if this thing would return a constant that we get, right? Here's synthetic token. So yeah, all we're doing is generating a brand new token. So that definitely belongs on token. All right, creating a new lexical scope. Oh, I didn't read this. Our compiler already emits code to load the superclass onto the stack. Instead of leaving that slot as temporary, we create a new scope and make it a local variable. Creating a new lexical scope ensures that if we declare two classes in the same scope, each has a different local slot to store its superclass. Since we always name this variable super, if we didn't make a scope for each subclass, the variables would collide. We named the variable super for the same reason we use this as the name of the hidden local variable that this expression is resolved to. Super is a reserved word, which guarantees the compiler's hidden variable won't collide with the user-defined one. It's a constant string because tokens don't do any memory management with their lexeme. If we tried to use a heap allocated string for this, we'd end up leaking memory because it never gets freed. But the memory for C string literals lives in the executable's constant data section and never needs to be freed, so we're fine. All right, the difference is that when compiling this expressions, we conveniently have a token sitting around whose lexeme is this. We aren't so lucky here. Instead, we'll add a little helper function to create a synthetic token for the given constant string. All right, so this will go in token. And do we have a new? We have a default, and we have a clone. So let's create a new simple token. Token. I guess we don't care about the token type. And there is no super, right? Oh, there is a super. Oh, we might as well shove it in there, right? T-type is token type. Super token dot lexeme equals super to string. And oops, I misspelled lexeme. And then finally, length we don't care about. Line number. We need a line number, don't we? Maybe we don't, because we're never going to report an error against it. All right, so that's that. Oh, just dot. Okay. And a colon. Wow, that was bad. Okay, there we go. So now we have to, oh, I call it synthetic. Let's just say new. Oh, right, duh. We need a name. And I just put it there, but we can put it here, right? And then we just put an ampersand there, and we're all done. Nope, we're not all done. Now we're all done. Okay, so that did it. So now we can generate a super or any other token we want. Although I did hard code super in here, didn't I? I guess I could put undefined for now, but we got it. Okay, we'll see. We'll see how they do it. I'm gonna leave it as super. And then after we emit the pop, has superclass. And that's going to be a Boolean. Okay. Which we have to set somewhere. This is all in class declaration. So why does it have to be part of? I'm just thinking, we just set a flag here. Let has superclass equals false, right? And then set it to true here. And then, we'll probably need it for other error checking. Okay. So we don't do it this way then. We're going to look at where we create this thing, this class compiler. it just has enclosing, and we'll add a bool. Oops, a has superclass ref cell bool. And it should default to false, and then we just set it to true here. Self. Oh, we have to go through this whole rigmarole now. Current class borrow has superclass replace true. And then we check that here just before and just after the pop. Where's our pop? There it is. So we can just say if, get rid of those lines, if self current class borrow has superclass borrow. Right, and then we're going to end scope, self end scope. All right, does that type check? No. Oh. Has superclass false. Ref cell new false. Okay, and what's wrong here? Unknown field. Oh. Do I do it this way? No. What am I missing? There's a step I'm missing. Self current class borrow. Oh, I have to unwrap it because it's a it's an option. Now we have a move. Oh, right. We have to do the as ref. And we have to do it here too. Yeah. Okay. Well, that's a pain. I wonder if we should just clean that up. I don't know if there's an easy way to clean it up. I was thinking, well, on current class we could make, or on the compiler code we could make some helper functions to help with all this mess. But I think this does the trick. Right? It's kind of long and unwieldy. Look at all this. Okay. This machinery gives us the mechanism at runtime to access the superclass object of the surrounding subclass from within any of the subclass's methods. Simply emit code to load the variable named super. That variable is local outside the method body, but our existing upValue support enables the VM to capture that local inside the body of the method, or even in functions nested inside that method. So this section here adds storing superclasses, but it doesn't actually do anything with them because it's not going to work, right? We still can't run it. Cargo run tricky. Yeah, because we're not parsing it yet. Okay, so I'm not going to commit these changes yet because they don't work yet. Supercalls. With that runtime support in place, we are ready to implement supercalls. As usual, we go front to back. Starting with the new syntax, a supercall begins naturally enough with the super keyword. This is it, friend. The very last entry you'll add to the parsing table. Okay. Yeah. So we added this, and now we'll add super. And super has only that one entry and prefix. So we change this to super, and we change this super. Okay, so super And does it use can assign? No. So underscore colon bool. Consume token dot self consume token type dot expect dot after super and self consume token type identifier expect superclass method name. Okay, and then let name equals self identifier constant. How do we do this? Where else do we use this? Ampersand name. Oh, right, I have to do it in these two steps. Okay. That's the way to do it. And then we have to save that. Name token and let name. Okay. This is pretty different from how we compile this expressions. Unlike this, a super token is not a standalone expression. Instead, the dot and a method name following it are inseparable parts of the syntax. However, the parenthesized argument list is separate, as with normal method access lock supports getting a reference to a superclass method as a closure without invoking it. Hypothetical question. If a bare super token was an expression, what kind of object would it evaluate to? Maybe just the superclass? Just like the superclass's name? In other words, Lox doesn't really have supercall expressions. It has super access expressions, which you can choose to immediately invoke if you want. So when the compiler hits a super token, we consume the subsequent dot token, and then look for method name. Methods are looked up dynamically, so we use identifier constant to take the lexeme with the method name token and store it in the constant table, just like we do for property access expressions. Here's what the compiler does after consuming those tokens. Okay, so we're going to say self-named variable token new this. Okay, so this is why we don't want the token type to be wrong. Self-named variable token new super false. Self emit bytes op code get super. Oh, we got a new opcode. I thought we were all done with the opcodes. Okay, so let's go over here and just set this to undefined. Because that's one of them on there. I guess I could also pass it in. Nope, that should be underscore. Name token. And these need ampersands. Almost there. Expected token, but got token. Okay, and we still have this error because we don't have get super. Okay, in order to access a superclass method on the current instance, the runtime needs both the receiver and the superclass of the surrounding method's class. The first named variable call generates code to look up the current receiver stored in the hidden variable this and push it onto the stack. The second named variable call emits code to look up the superclass from its super variable and push that on top. Finally, we made a new op get super instruction with an operand for the constant table index of the method name. There's a lot to hold in your head. To make it tangible, consider this example program. So let's copy this as a super although it's not so I guess we could say var c equals, right, and then just say c cook. And that should get us icing. Whereas if we grab this as donut, that should just say finish with sprinkles, and this should say finish with icing. Right? This isn't going to work yet because I don't think we've got it wired up. Oh, we don't even have compiling yet, right? Because we don't have a get super. Okay. The bytecode emitted for super finish icing expression looks and works like this. So we get local, get the up value. We get super for finish. We get the constant on icing and then call nil. I guess it returns nil. The first three instructions give the runtime access to the three pieces of information it needs to perform the super access. The first instruction loads the instance onto the stack. The second instruction loads the superclass where the method is resolved. Then the new op gets super instruction encodes the name of the method to access the operand. Access an operand. The remaining instructions are normal bytecode for evaluating an argument list and calling a function. We're almost ready to implement the new get super instruction in the interpreter, but before we do, the compiler has some errors it's responsible for reporting. Alright, so if a current class is null, can't use super outside of a class. So that's the self, right? It's if self.currentClass.borrow is none. Right? Let me see where else we use that. Yeah. Right. So we can do that, and we can just say self error can't use super outside of a class. And then else if it doesn't have a superclass. So now we have to go through this self current class borrow as ref unwrap. Oh, so there's a better way to do this, right? Has superclass borrow. Right, that's this self error can't use super in a class with no superclass. Otherwise we just but then we carry on. Okay. That should compile, but I think we can do better, right? And we still don't have get super. That's fine. But I think what we can do is just say match self current class borrow. If it's none, then we report this error. If it's some option, if it's some class compiler, then we can just say if cc dot all of that, right? And then close the map that way. Does this compile?
I think that's pretty.
No. Oh, as ref. Star? Yeah, star. Okay. Yeah, that did the trick. Okay, so I think that's a little bit cleaner than what we had before. Right? Yeah, I think so. The supercall is meaningful only inside the body of a method or function nested inside the method, and only inside the method of a class that has a superclass. We detect both of these cases using the value of current class. If that's null or points to a class with no superclass, we report those errors. Assuming the user didn't put a super expression where it's not allowed, their code passes from the compiler over to the runtime. We've got ourselves a new instruction. Is this the last one? To 35 of these guys. Actually 36, right? Opcode get super. We disassemble it like other opcodes that take a constant index table operand. Okay. You might anticipate something harder, but interpreting the new instruction is similar to executing a normal property access. Let's hop over to here. Opcode get super. So it's similar to normal property access, which means it's going to be like get property, right? That's not uncomplicated. All right, so we're going to grab, or we're going to do a read string, and how we do read strings is special. I'm just looking up here to see how we do it. This is how we do it. Constants, and then we get the superclass. Oh no, this is the name. Right, and then we're going to pop the class. Does self pop return? It returns an RFC ref cell value. Okay. So we can say let superclass equals self pop. And then there's bind method. Ah, this is similar here, right? Okay. If not self bind method, superclass name return self runtime error. Oh, we're just returning the error. Error interpret result runtime error. We don't report anything, and then we're done. All right, so what fails here? Expected class found struct ref cell. I guess we could say borrow, maybe? Here? Can we? So this is a ref cell to a value. Oh, we have to extract the what is bind method expecting? It's expecting an RC to a class. So if self pop value class equals self pop. Oh, that's not going to work either, right? Borrow. I wonder if that's going to work. Class. Otherwise, I'm going to report an error. For now, no superclass. And I think there'll be code in the future with this document which has that as a specific error, right? Oh, if let. Expected struct ref found enum value. Because it's a ref to a value. sref? No, I can't do that, right? Or dref? No. Oh, the trait's not in scope. Use standard ops dref. And now we can't do this because it's already a class, so I don't have to borrow it. And now the borrow checker is going to kill me, right? Oh, expected struct RC. Oh, it's a reference. And that won't work, right? Oh, it does. Oops. Yeah, temporary value dropped while borrowed. So I think I have to do the same thing I did before, is pop value is equal to this. And then pop value. Nope, doesn't like that. Oh yeah, it's still a temporary, so I have to clone it instead of deref it. And now this doesn't get derefed anymore. And we've got 2 warnings that we're not using deref. Okay. Whoops. There. Okay, I think we're there. Oof. As with properties, we read the method name from the constant table. That's what we're doing here. Then we pass that to bind method, which looks up the method in the given class's method table and creates an object-bound method to bundle the resulting closure to the current instance. The key difference is which class we pass to the bind method. With a normal property access, we use the object instance's own class, which gives us the dynamic dispatch we want. For Supercall, we don't use the instances class. Instead, we use the statically resolved superclass of the containing class, which the compiler has conveniently ensured is sitting on top of the stack waiting for us. We pop that superclass and pass it to bind method, which correctly skips over any overriding methods in any of the subclasses between that superclass and the instance's own class. It also correctly includes any methods inherited by the superclass from any of its superclasses. Another difference compared to opt-get properties is that we don't try to look for shadowing a field first. Fields are not inherited, so super expressions always resolve to methods. If locks were a prototype-based language that used delegation instead of inheritance, then instead of one class inheriting from another class, instance would inherit from, delegate to, other instances. In that case, fields could be inherited, and we would need to check for them here. The rest of the behavior is the same. Popping the superclass leaves the instance at the top of the stack. When bind method succeeds, it pops the instance and pushes the new bound method. Otherwise, it reports a runtime error and returns false. In that case, we report the interpreter. Okay. And now before I go to faster supercalls, so that should have been, this section should have been part of the previous section, right? Because now we actually have them working, hopefully. So I should be able to run this, cargo run super. Can't use super in a class with no superclass. Okay, so we already have a failure. And that was on line 15. Which I can't do, can't dash in. Okay, for some reason it doesn't see the donut as a superclass, so that means our setting and whatnot isn't working. Oh, that's in the compiler. And then where do we check it? And then where's the begin scope? Here it is, but then begin scope. Class scope, right? Here's has superclass. We set it to false. There. And then let's print. Can I print this out debug? Yes. Okay. So cargo run super. Let's see what we get. We get begin class scope. Setting has superclass to true. And it's set to true. Oh, did I flip the test around? Oh, I did. That was dumb. Okay. If I just looked at the code instead of started to go right to print debugging, we would have seen it. All right. Dunk in the fryer, finish with icing. Here's dunk in the fryer, finish with sprinkles. Okay, and let's take a look at the code. This is the cook code, the finish code. The finish code for... These are for donut, and this is for cruller. Now there was a problem with the method inheritance, right? Here's op inherited and left donut on the stack, and I still see donut on the stack, but it disappears here after the call. So maybe it's okay. I mean, it must be okay, right? That we can do that. Oh, when we close up value, that's when it disappears. Interesting. Wonder why we weren't seeing that before. But looks like it's working. Cargo, run cook. Yeah. Cargo run tricky. And prints out a method, which is, as if I remember correctly, that's the correct thing it needs to do. C calls C test. C test is B's test. B test calls super method. Method prints a method. So that's working. All right. So let's check this in as superclass method calls. Where it is, supercalls. Git add source, git commit, sections 29.2 and 29.3 supercalls. Oh, see, I thought I complained when I took out the 708, 709, and 934. Uh, 934. There. Okay. Now it's not complaining. I must have misread the error message then before. Okay. So we did all this. It's faster supercalls, right? Okay. We have superclass method accesses working now. And since the returned object is an object-bound method that you can invoke, we've got supercalls working too. Just like last chapter, we've reached a point where our VM has the complete correct semantics. But also like last chapter, it's pretty slow. Again, we're heap allocating an object-bound method for each supercall, even though most of the time the very next instruction is an op call that immediately unpacks that bound method, invokes it, and then discards it. In fact, this is even more likely to be true for supercalls than for regular method calls. All right, I guess what we can do is write a little super time. All right, we'll say class A, and we'll have method foo, which doesn't do anything. And we'll say class B inherits from A. And then we'll say bar, which calls super.foo. Right? And then for bar A equals 0, A is less than, let's say, 1,000,000. A equals A plus 1. Oh, let's do this. Var B equals B. B dot bar. Right, so that tests the time of calling a super thing. And then we're going to start. Var start equals clock. Print clock minus start. Cargo run. Release. No default features. Super time. All right, 2748 for 1,000,000 supercalls. All right, so remember that number. At least with method calls, there is a chance that the user is actually invoking a function stored in a field. With supercalls, you're always looking up a method. The only question is whether you invoke it immediately or not. The compiler can certainly answer that question for itself if it sees a left parentheses after the superclass method name. So we'll go ahead and perform the same optimization we did for method calls. Take out the 2 lines of code that load the superclass and emit opGetSuper and replace them with this. Super invoke. Okay. So opGetSuper. Oh, get super. There it is. Oh, okay, so it must be these 2 lines here, right? That we're going to replace. And we're replacing with if self is match token type left paren right? Let arg count is equal to self argument list. Self named variable is token new super false. Self emit bytes opcode super invoke like that with the name. And then self emit byte arg count. Else what we had before. Right? Right. That's interesting. I wonder if we could just lift this out. Right, because we have this line here and here. Do we need to do this before we do the name variable? Maybe. Maybe that's why it's done like that. Now, before we emit anything, we look for a parenthesized argument list. If we find one, we compile that. Then we load the superclass. After that, we emit a new op super invoke instruction. This super instruction combines the behavior opGetSuper and opCall. So it takes 2 operands, the constant table index of the method name to look up, and the number of arguments to pass to it. This is a particularly super instruction. If you get what I'm saying, I'm sorry for the tolerable joke. Okay, otherwise, if we don't find a left paren, we continue to compile the expression as a super access like we did before and emit an opGetSuper. All right, so now in chunk, we're going to add super invoke and just pass that this disassembler in support. So 36 is op code super invoke, and this is going to be an invoke instruction. Like that. A super invocation instruction has the same set of operands as op-invoke, so we reuse the same helper to disassemble it. Finally, the pipeline dumps us into the interpreter. All right. Which is, nope, didn't like that. P-A-R-E-N. There, okay, opcode super invoke. And this is going to do what? Read string, read byte, superclass, invoke from class, and then reset the frames. Okay, so it's kind of like invoke. Let's copy paste invoke and then edit as we need it. Okay, so we're going to read the string, which is the method name. We get the arg count as read byte. And then we have this invoke from class call. we do need to do this. We say as class pop for the superclass, which is this code here. And this is going to return error, interpret result, runtime error, like that. And then we're going to, instead of calling invoke, we call invoke from class. Which already exists. Okay. So if not self invoke from class, we give it the superclass, the name, and the arg count. Like that. Does that build by any chance? Of course not. Run tim error. Method name's right here. There. Look at that. This handful of code is basically our implementation of op invoke mixed together with a dash of op get super. There are some differences in how the stack is organized, though. With an unoptimized supercall, the superclass is popped and replaced by the obj-bound method for the resolved function before the arguments to the call are executed. This ensures that by the time the op call is executed, the bound method is under the argument list where the runtime expects it to be for the closure call. With our optimized instructions, things are shuffled a bit. The superclass is over here. Okay. Now resolving the superclass method is part of the invocation, so the arguments need to already be on the stack at the point that we look up the method. This means the superclass object is on top of the arguments. Aside from that, the behavior is roughly the same as an op-get-super followed by an op-call. First we pull out the method name and argument count operands, then we pop the superclass off the top of the stack so we can look up the method in its method table. This conveniently leaves the stack set up just right for a method call. We pass the superclass method name and argument count to our existing invoke from class function. That function looks up the given method on the given class and attempts to create a call to that with a given arity. If a method could not be found, it returns false, and we bail out of the interpreter. Oh, John YW001, thank you for the follow. That invalidates the interpreter's cached call frame pointer, so we refresh frame. Which I don't have to do because I handle it differently. Okay, so does that run any faster? The old one was 2748, and the new one is, drum roll please, 2263. So yeah, about 20% faster maybe? Sort of? We finally got an optimization that makes things more optimal. Okay, so that was section 29.3.2, faster supercalls. All right. Wrapping things up, a complete virtual machine. Oh, we're done. Good. That's perfect timing too, because I'm done with my stream. Take a look back at what we've created. By my count, we wrote about 2,500 lines of fairly clean, straightforward C. By my count, we have 3,000 lines of Rust. Okay. That little program contains a complete implementation of the quite high-level LOX language with a whole precedence table full of expression types and a suite of control flow statements. We implemented variables, functions, closures, classes, fields, methods, and inheritance. Even more impressive, our implementation is portable to any platform with a C compiler and is fast enough for real-world production use. We have a single-pass bytecode compiler, a tight virtual machine interpreter for our internal instruction set, compact object representations, a stack for storing variables without heap allocation, and a precise garbage collector. Yeah, so this 3,000 lines of Rust does not include a garbage collector or any of the memory allocation code. So yeah, that's pretty impressive for C, right? If you go out and start poking around in implementations of Lua, Python, or Ruby, you will be surprised by how much of it looks familiar to you. You have seriously leveled up your knowledge of how programming languages work, which in turn gives you a deeper understanding of programming itself. It's like you used to be a race car driver, and now you can pop the hood and repair the engine too. You can stop here if you like. The 2 implementations of locks you have are complete and full-featured. You built a car and can drive it wherever you want now. But if you're looking to have more fun tuning and tweaking for even greater performance out on the track, there's one more chapter. We don't add any new capabilities, but we roll in a couple of classic optimizations to squeeze even more performance out. That sounds fun. Keep reading. Yeah, I will do that. Not today, though. Today, I'm going to actually go over here and not here. Oh, yeah, that's right. I've lost my, after a reboot, I lost my window that runs Dart. It's under crafting interpreters. What I wanted to do is run Dart and see how bad we are. And this is going to be locks, bytecode, target, release, locks, bytecode. I do want to rebuild it though. Cargo, build, release. I can do this. Cargo, build, yeah. Oh, I already built it? Oh, right, because I ran a performance test. Okay, so it's built. So let's see how bad it is. 44 tests failed. Okay. All right, so that'll be one stream. Error at VFF, to do, error message. Error at oops, to do, error message. Oh. I left a to-do in there? Wow, I did. Why? Why did I do that instead of actually putting the too many variables? I wonder if that'll fix at least a couple of errors. I'm not going to go through all the errors. So I was just curious about that to-do one. What do we got? No, it still has 44 errors, so I didn't fix it correctly. All right. Well, we'll go through those. Not now. Tomorrow we will... Ooh. What are these? A tenet of object-oriented programming is that a class should ensure new objects are in a valid state. Oh, they're asking how would you address field. All fields are public in locks. So a copy down inheritance optimization is valid only because locks does not permit you to modify classes methods. So I'm not going to think about that one either. In the JLocks in chapter inheritance, we had a challenge to implement the beta language's approach to method overriding. Oh, okay. All right, I'm not going to worry about that. The next thing we have is optimization, but I think tomorrow I'm going to go back to my editor here. We're going to work on the enter key, because right now we can't enter new lines in the editor. Right there. Make this a little smaller. Right, because if I go here and try to edit a file and hit the enter key, it doesn't work. So that's something we're going to fix here. All right, that's tomorrow though. Today was the end of that chapter. We finished chapter 29. We started and finished chapter 29, so that's great. I hope you enjoyed the stream. I had a lot of fun doing this. And I will see you next time with the enter key. Sounds very exciting. All right. I'll talk to you later. Take care. Goodbye.